we would reject L3 as well, right? Because it is in the opposite hemisphere. Now, let's say we found the L that we want. Okay, we could make a few tries, and maybe we end up rejecting a couple of candidate vectors, but eventually it will not take a long time until we find something that fits these conditions. Then what we do is, if these conditions hold, okay, if these conditions hold, we will basically return our direction vector. But the direction vector, we will make it a unit vector. We will normalize it. Okay, so we are going to return L divided by the magnitude of L. If L satisfies both of these conditions. If L doesn't satisfy these conditions, okay, now else, if we fail to satisfy these conditions, we go back to step 1. Okay, in this step, we again try another one. So the reason that rejection sampling is slower than alternative methods is because you end up rejecting some samples. Later we will learn a technique known as inversion sampling, which makes this thing much faster. So after we compute our L, okay, what are we going to do? First of all, in the last week PowerPoint slides that I shared, we have learned about HDR imaging. Okay, so one of the uses of HDR images is as environment maps. Okay, HDR images can be environment maps because they can represent the high dynamic range lighting in a given environment. So once L is chosen, okay, once L is chosen and normalized, okay, to be a unit vector, okay, we use it to look up a pixel from the environment map. Environment map. Okay, this environment map will be an HDR image. So these images are generally these environment maps, in order for them to represent the lighting correctly, they are represented in latitude, longitude format. Okay, so they are not just like regular images. They are regular, but they are projected on a rectangle by warping the rectangle, so basically they are a projection of a sphere onto a rectangle. Okay, so when we look up a value in them, they represent a direction instead of just representing some value that does not match to that direction. So the images that we use will be in latitude longitude format. I will share some images with you, and there are also many images online. Now once we have L, we must map this to a direction. Okay, so this is L, right? Remember, and remember we have our normal, surface normal, and two other vectors. Okay, so you can think of them like U and W. So this is our point P. This was the surface normal at point P, and L is we have generated using the procedure in the previous board. Okay, so what we do is we will now generate the texture coordinates to look up the environment map. Okay, so remember, let's remember our angles here. Okay, so we have two angles, theta angle and phi angle. So here we have a coordinate system, which is so you can think of this like U, W, and N. The N vector is like our V, okay, UVW coordinate system. And here we will be using to compute this angle theta. Okay, note that this is a unit vector. We have normalized it. So theta can simply be found. So we know that here, if you like look at this part, Okay, so this is this direction is L dot V. Okay, L dot V. So, and this distance, let me use a different color. This distance is 1 because L is a unit vector. So here we can say, we can see that, we can see that cos theta is equal to L V, the second component, divided by 1 hypotenuse. So theta is equal to cos minus 1 L dot V, the second component of L. Similarly, phi can be found, okay, I will not write the derivation, but phi can be found as inverse tangent L W divided by L U. Okay, just like the same as in texture mapping. So we find two coordinates, theta and phi, and now we convert them to u and v as usual. So u is equal to minus phi plus pi divided by 2 pi, and v is equal to theta divided by pi. So the same, we are using the same kind of mapping. Okay, we are using the same kind of mapping as we did in texture mapping. Now, once you have the UV values, we sample the HDR image, which is the environment map, okay, using the UV texture coordinates. And that becomes the radiance value that you get from that direction. So this will give us L. The value that we read from the HDR image is going to be the radiance value. Actually, HDR images are also known as radiance maps. So this radiance L, but again, similar to area lights, we have sampled only one direction. Now, for that direction to represent the entire illumination, we must do some normalization. Okay? So what we do is we must divide this radiance by the probability of selecting this direction. Okay? So what is the probability of selecting L? Probability of selecting L was, so we have been uniformly sampling directions from the hemisphere, upper hemisphere, from here. Okay? So this upper hemisphere has the total solid angle of half sphere is 2 pi. Okay, so the probability of selecting one direction in this like half sphere or upper hemisphere is 1 over 2 pi. Okay, so what we are going to return is going to be this. So let me clear it here and write it here. The illumination, the contribution that we are going to make in this point, towards this point, okay, towards this point is going to be L divided by 1 over 2 pi. Okay, so we divide the value by the probability of selecting this. The same idea that we have done in area lights. Okay, and this is going to give us L times 2 pi. So this concludes our discussion on more advanced types of lights. The only thing that we didn't talk about are the object lights. So the object lights could be like spheres, or they could be like triangles or meshes. Okay. In order to learn about them, first we need to learn about more properly learn about sampling, randomly sampling a point on an object, things like that. So today we did this a little bit here for sampling like area lights, but we will discuss it more thoroughly in later lectures. Okay,